Good morning, everyone.
Morning.
Welcome. Start my recording. So these talks are being recorded, and I will eventually have them all up on YouTube. I brought a friend. I hope some of you did as well. This is Albert. We're going to talk about some of Albert's ideas today. This is one of my favorite topics today. It's relativity. And I first became enamored of relativity in junior high. And I actually brought one of the books that I read. I think I read this in high school. But the librarian was so much in favor of my pursuit of scientific interests that he sold me this book out of the library. And I've still got the original purchase receipt on it. So in 1981, so proving that my interest in relativity goes back quite a ways. So relativity is very interesting, and one of the reasons I think it's particularly interesting is because it's incredibly counterintuitive. And it has implications for the way that our world works that are very surprising and yet quite subtle at the same time. And we're going to talk about some of those today. So the first notion of relativity was promulgated by Galileo. And Galileo thought a lot about ships. He didn't necessarily think about ships in this kind of context where seas are stormy and things are being tossed around. Rather, he thought about ships in this kind of context where they're big ships on calm seas. And if you look carefully on this ship, you'll see basketball courts and tennis courts and swimming pools and diving boards and all kinds of activities that you can engage in on this ship. Interestingly enough, you can engage in these activities while the ship is moving. So if you jump off of a diving board, let's say you jump up, prepared to hit the water in the pool below you, you don't have to worry about the ship moving out from under you while you're up in the air, right? This kind of observation led Galileo to recognize that, in some sense, the laws of nature remain the same even if you're in constant motion. If you throw a ball up, you can catch the ball again, even if you're on a moving vessel or a moving spaceship, etc. And this recognition about the constancy of the laws of nature in a moving reference frame has some interesting implications. Here's an example of an airplane flying entirely too low by this person. And the person that may be standing in the aisle of the airplane can throw a ball up and it comes right back down to his hand, and that's what he sees. But somebody watching that procedure from the ground will see the ball go up and describe this very long arc. So it takes a longer path than the person on the plane might say it takes. And yet both of them can apply the laws of physics about momentum and the force of gravity pulling things down and how fast its trajectory is up and how fast its trajectory is to the side. This guy says the side trajectory is very little. This guy says the side trajectory is quite a bit. But when they calculate the momentum and the energy, the physics, the values that they come up with all work out. You can do the same from a terrestrial context. If you're throwing a ball up on a back of a vehicle that's moving very smoothly, then you can just you can juggle or whatever. But somebody on the ground would see this very large trajectory. Same thing happens in the context of moving ships. If you were to drop a cannonball from the top of a mast on a ship that's being blown ahead quite rapidly by the wind, then in some sense the cannonball can be seen to describe this trajectory as it falls down. And some things are not identical between observers. The person who's stationary versus the person who's moving along with that vehicle or vessel will see that the velocity of the projectile changes. Maybe the mass times the velocity, or the momentum will change. The energy, which in some sense is velocity squared times mass, will be different. And then, interestingly enough, electromagnetic phenomena are particularly different if you're in a moving reference frame. You may have learned at some point that moving charges give rise to electric fields. Well, what if you're moving along with the charge? Where's the electric, or where's the magnetic field? We're going to talk about that. So we have a precedent for disagreement between observers. Right, taking the case of electromagnetism specifically, if you're not moving along with a charge, you'll see a magnetic field emanating from that particle. But if you are moving along with it, you won't see a magnetic field. There's going to be some disagreement, even with Galileo's concept of relativity. So Einstein, who was elected, I don't know who the august body was that elected him, but he was elected, or I guess Time magazine said he was the person of the century for the 1900s. And partially because of his own personal work in relativity and quantum mechanics and thermodynamics, etc. But largely because Einstein is the exemplar of the scientific progress made in the 1900s, in the 20th century. At the beginning of the 20th century, people didn't use automobiles. There was no electrical wiring to speak of. There are all kinds of things that happened in this century, almost magical century, and he is the exemplar of some of the amazing progress that science made. Einstein took Galileo's idea, and he recognized something about it that was potentially quite profound, and that is that the speed at which light moves through empty space is also a law of nature. Now, Galileo said all laws of nature remain constant or consistent regardless of whether you're in a state of constant motion or not. What Einstein recognized is that the speed of light must be one of those things that remains constant regardless of your state of motion. So if you're measuring the speed of light, let's say that you're in a rocket ship and you have some kind of device for measuring the speed of light, but if you're in a spaceship that's moving along and you take your laser and you shine it up towards the ceiling and then it bounces back down, you can measure the speed of that light because you know how far it is to the ceiling and you know how far it is back down and you know how long it took. So that's speed. Distance over time is speed. And he'll come up with a measure of the speed of light. This lady here who's watching this through a portal in her own spaceship that is perhaps at rest with regards to this one, or she sees this one moving by, what she'll see is when this fellow shines the laser up to the top of the cabin and then it comes back down again, it takes a much longer path. Right? We can see that. And yet when she measures the distance it's traveled by the time it took to travel that distance, she comes up with exactly the same number. Well, in a very profound way, that doesn't make any sense, right? It's counterintuitive. Why should people who have very different measures of what's clearly a different geometric configuration, why would they agree on the ultimate outcome of that experiment? We said before that if you're moving along with an electron, you don't see a magnetic field, but if you're not moving along with a speeding electron, you do see a magnetic field. We've become accustomed to seeing different results for different observers, as long as their own observations are internally consistent. But here we see clearly an example of a measurement of a physical phenomenon where they absolutely do agree. And yet the situation is quite bizarre. So Einstein took this notion of Galileo's that all the laws of nature must be the same, even if you're in constant motion. And he recognized that the speed of light must be one of those laws. So what is relativity not? Right? Relativity, Einstein wanted to call relativity the theory of invariance, because the speed of light is invariant, it doesn't change. Other people came up with the notion of calling it relativity. And a lot of times in our popular culture, the very vocabulary that we use to describe science has been co-opted for non-scientific purposes. Relativity is one of those times when the vocabulary can mislead us. Relativity does not say all points of view are equal. Relativity does not say that everybody's free to interpret reality however they wish. Relativity says none of those kinds of things. Relativity might say that the view that one observer has compared to the view of another observer might be completely different. But those are because of underlying differences that they experience about the way the world works, whereas the way the world works is internally quite consistent. You can see that there's a light shining on this round peg, and if you view it this way, it looks like a round shadow, and if you view it this way, it looks like a square shadow from the same round peg. It says nothing about phenomena, opinions, or data that does not involve physical properties of observables. So it doesn't say anything about ethical relativism, right? Some people in the social sciences have used this term of relativism to talk about moral relativism or ethical relativism, and that has nothing to do with Einstein's theory. It may in of itself be logically persuasive or have some valuable content, but it has nothing to do with Einstein. So people who write self-help books and co-opt this term of relativity to talk about you're free to choose your own interpretation of reality, etc., that's just nonsense. And we're going to talk more about that kind of nonsense next month when we talk about quantum mechanics. Relativity is described with mathematical language, and in some extreme cases, we are absolutely certain that the math fails to describe reality in extreme circumstances. Here's an example. Electromagnetism is, in a very profound way, a direct result of relativity, and we'll talk more about that in a few minutes. But one of the predictions of electromagnetism, and hence of relativity, is that when an electron is moving around an atom, that because it's moving in a circular path, it must necessarily emit radiation, because an accelerating charge, or a charge changing its direction over time, or a charge changing its speed over time, anything that constitutes an acceleration, will cause that electron to emit light. And yet, atoms don't decay in a few thousandths of a fraction of a second. We know that atoms are stable. So something is a little wrong with relativity insofar as, in extreme cases, there are times when the mathematics of relativity tells us what might be happening, and those conclusions cannot be true. The path of an electron around an atom has more to do with quantum mechanics and something called the wave function, and fitting an integral number of wavelengths into the orbit of an electron. We'll talk more about that next week. There are also extreme cases around things like black holes, where the equations of relativity say that once you pass a particular boundary around a black hole, that time will start running backwards, and maybe your mass, the amount of mass you have, becomes imaginary. Remember those Lama numbers that some of you might have been here when we were talking about imaginary numbers? There are some of the solutions to the equations describing relativistic phenomena that give absurd results in some cases. But for many cases, the results that come out of the math are surprising and they're counterintuitive, and we've done all kinds of experiments to show that they are in fact real. So why is light so special? Why do we talk about the speed of light being interesting and not in the same way the speed of sound may be interesting? Well, one of the reasons, in fact, the fundamental reason, I might say, is because sound propagates through a medium. If you're underwater, the speed of sound from whales singing is different than the speed of sound in air. And the speed of sound and the vibration of a string between cups and strings is different. And the speed of sound in a metal bar is different. So the speed of sound varies based upon the medium in which it travels. And unlike many space movies, if you make a sound, if you vibrate your vocal cords out in space, Perhaps you're screaming because you're out in space with no atmosphere. No sound will come out of that. Sound necessarily requires a medium in order to transmit. Well, light is different. Light is self-reinforcing. It's an electric field that changes over time, that creates a magnetic field that changes over time, that creates an electric field. It's self-propagating. And it'll do this without any medium to go through. And the equations of electromagnetism very clearly say what that velocity of self-propagation should be. And it's not dependent upon anything else in the universe, generally. There's some exceptions when you talk about the refractive index of a translucent or transparent material. But even then, as the light travels in between the atoms in that material, it's still moving at the same speed of light. It's just absorbed and re-emitted really quickly, with the effect being that light seems to slow down from our gross senses standpoint. So the speed of light doesn't propagate through anything except space. And the only thing that can make the speed of light seem to change is if space or time changes. And we'll talk about that. The speed of light is a fundamental attribute. I discussed that. Why does light constancy have to do with no information being able to be sent faster than light? You perhaps have heard that nothing can communicate faster than the speed of light. Well, why is that? Well, in order for communication to happen, you must transmit some kind of matter or energy from me to you. Right? In this case, it happens to be energy of sound waves, which we've said is much slower than the speed of light. But in any conceivable mechanism that you may try to invent, you must necessarily invoke the transmission of energy or matter in order to communicate. And relativity says that the speed of light is always the same, no matter how fast you're moving. And one of the implications of that, we'll talk about in the next couple of slides, is that there's no way you can ever perceive something to go faster than light. Because you always have, no matter how fast you're moving, you always have to be able to measure the same speed of light. The classic thought experiment is you're on a train, and you shine a flashlight ahead of yourself on a train that's moving nearly the speed of light. How fast does that flashlight beam propagate out in front of you? Well, from your point of view, on the edge of that train, that flashlight beam goes out at the same speed as if you were standing still. And that's very counterintuitive. We'll talk about some of the details of that in a moment. So the implications are that these ideas that we have about space, the distance between things, or time, become in some way conflated. And space and time, in some sense, become interchangeable. The same thing can happen between energy and matter. We'll talk a little bit about the E equals mc squared implication of relativity in a few minutes. But the notions of space and time get conflated into a single thing called space-time. Now that's not particularly surprising to those who study science, because one of the things that science, and especially physics, does is, contrary to what you may perceive with new things being discovered all the time, and new particles being discovered, and new forces of nature being discovered, which I hope has stopped. I think we're at 4, and I think that's all we're going to find. But contrary to what you may think about science is always discovering new things, physics is particularly interested in understanding how all of these myriad things we see in the universe about us are related to very basic fundamental properties. Right? Some of us went to the dark matter talk at Fermilab last Friday, and one of the things that he used as an example of this is the periodic table of elements, which has 92 naturally occurring elements. But all of those elements are made of 3 basic things: electrons, protons, and neutrons. So out of 3 things, we get at least 92 elements, and the interactions between those elements comprise the chemistry that creates our world. our biochemistry, the chemistry of our computers, etc. So with 3 little particles, you can explain in principle the behavior of almost everything in the universe. If you add into it a few other particles, which we'll talk about in a couple months. So one of the things that science has done is, back in the 1800s, we were able to unify the concept of magnetism and electricity, and we found that there was a single underlying phenomena that gave rise to both electricity and magnetism, that they were inseparable. They were different aspects of the same beast, as it were. Well, the same thing is true for space and time. Space-time is a thing in of itself, but talking about space, irrespective of time, or vice versa, becomes challenging once you get beyond our intuitive, slow-speed world. And in fact, interestingly enough, there's this idea that, well, where's my pointer? There it is. So I can give it this. There's this idea that in order to move through space at all, in order to not be standing still, you have to give up a tiny bit of motion through time. So space and time are interchangeable necessarily. You don't see that effect at the scale of everyday things. If I want to walk at a particular speed and you're watching my hypothetical wristwatch, you're not going to see anything remarkable. But as I move faster, ever closer to the speed of light, what you'll see is that in order to move faster through space, my motion through time relative to yours becomes slower. And that's one of the reasons that I can't go faster than light, is because as I'm moving faster and faster, I stop moving through space so much, and I instead exchange that for moving more slowly through time. So the idea of space and time are intimately linked. And I want to leave a lot of time for questions at the end of this talk, so that some of you that have questions might be able to explore that more deeply if you wish. But in general, in order to make something move faster, you have to put energy in it. You have to accelerate it. And the amount of energy you would need to put into anything, whether it's an electron or a freight train or a planet, the amount of energy that you need to put into a thing to get it to move at exactly the speed of light is exactly equal to infinity. You need an infinite amount of energy to get to the speed of light. And that's the reason nothing that starts going slower than light can ever get to the speed of light, much less beyond it. After about 50% of light speed, so light speed is 186,000 miles per second, or 300,000 kilometers per second. Once you get to about 50% of that, a large and ever-increasing amount of the energy that you try to put into your rockets to make you go faster and faster is stored, in some sense, in your mass rather than in your velocity. And we'll talk about that in more detail in a moment. So here are some of the things that relativity causes to change. Remember that idea of the rocket ship with the light beam going up and coming back down? The only way that they can agree that the person in the rocket ship who sees it go straight up and straight down, and the person on the ground watching the light describe a large triangle or a large angle, the only way they can agree that the distance divided by the time it takes for that to happen comes out to exactly the same answer is if distance and time are different for the people that are in different moving reference frames. So if you're standing still with reference to this rocket, I don't know what happened. Probably pressed the button. I shouldn't have. Oh, it looks like the computer is shutting down. It is in fact shutting down. We'll see if Dave can configuring Windows updates. is at the speed of light is if the distance involved and the times involved, the ticks on the watch or the ticks along the meter stick are different for the person standing still or the person moving. So time and distance change as you move closer to the speed of light. And in fact, they change even if you move very slowly. But we don't notice it. Let me give you an example of that. I brought something to read, just in case the computer crashed. I borrowed this, and I edited it a bit for what I believe to be clarity. This is from a science author and blogger named Simon Field. He says, the general impression is that relativistic effects are not significant at lower speeds. That impression is wrong. The reason an educated person might have that impression is because of a little thing known as relativistic gamma, a function of the speed that becomes larger as you approach the speed of light. So I've got a picture of the gamma function. I can describe it to you just sort of standing here. So in general, when you're moving faster and faster in our regular everyday thoughts about the way velocity works, you can think of increasing your velocity as just increasing the slope of a line gradually. Well, what happens because of relativity is that it becomes shaped more like a hockey puck, this line of what it means to accelerate. The amount of energy it takes to go faster and faster becomes greater and greater. And the increase in your velocity due to ever-increasing energy, instead of it being a line that can just keep going forever off to infinity, it actually turns into a hockey puck and hockey stick, and it goes like this, and it approaches some finite limit, and that limit is the speed of light. No matter what you do, you can never get up to the speed of light. But that graph, the function that describes that, is called gamma. And that particular function has a value at very low speeds. It's just the value is so incredibly tiny you never notice it. So a person, an educated and a reasonable person, might have the impression that relativity is irrelevant because of a little thing known as relativistic gamma, a function of speed that becomes larger as you approach the speed of light. Gamma tells us how much time dilation will occur, how much heavier you will get, and how much thinner you will become as you increase your speed. The magnitude of the effects of special relativity is denoted by a term, this gamma term, which has a fairly simple equation. I would show it to you if I could. At low velocities, gamma is very close to 1, and it doesn't become 2, so what does it mean for gamma to become 2? It means your clock runs half as fast compared to somebody at rest. It means that the amount of mass that you exhibit anytime your mass might be measured is increased by a factor of 2. So, in order for gamma to become equal to 2, you must be going at 87% the speed of light. That's about, 145,000 miles per second. The fastest thing that humankind has ever launched into space, the fastest large object, is the Voyager spacecraft that's traveling about 30,000 miles per hour, I think. We've got a long ways to go between 30,000 miles an hour and 150,000 miles per second. Speed of light is really fast. One of the problems is that things out in the universe that we might want to visit someday, like some of these planets that might be habitable, are vastly far away. And I'll talk about that. Thank you very much, Dave. So speed changes, time changes, length contraction happens, and also mass increases happen, and gamma function. So here's the math I promised. Whoop, go back. That's the equation. It's actually simple algebra. This is the Greek letter gamma. And it's 1 divided by the square root of 1 minus your velocity compared to the velocity of light. And you square those things. It's a pretty simple, you can do it on Excel, right? It doesn't require a giant computer simulation to do this. You can do it on a handheld calculator. And in fact, you can plot this gamma curve. I'll get to that in a moment. So the magnitude of the effects is denoted by a term called gamma. At low velocities, gamma is very close to 1, and it doesn't become 2 until you're going nearly 90% the speed of light. However, as the speed gets ever closer to the speed of light, gamma gets very large, quickly racing past factors of 10, or 10,000, or 10 trillion. So gamma starts off very gentle at any speed we can acquire up to even half the speed of light. We don't see many changes due to relativity, so we think. I'm going to give you an example of how we're wrong about that in a moment. But gamma doesn't become particularly noteworthy until we're about 90% the speed of light, and then it just almost goes vertical in terms of its value. At normal human speeds, such as walking, surely gamma is so close to 1 that we can ignore it, right? Well, no. This is one of the most beautiful things in science, in my opinion. It turns out that if you have something that is very small, it can be important if you have a whole lot of them. An atom might not weigh much, but an elephant is made of a lot of atoms. And there are a lot of electrons in a compass needle or a wire. Magnetism seems like magic sometimes, but it is really just a whole bunch of electrons moving very slowly, and showing us how relativity can happen not at starship speeds, but at walking speeds and below. Consider the electrons moving in an electric wire, maybe a lamp cord. Those electrons in general are moving about 50 times slower than, any guesses? 50 times slower than the speed of light, it's a good guess.
50 times slower than an airplane?
50 times slower than an airplane?
Speed of sound.
That's a good guess too. These are all guesses that I would have potentially, had I not gone through physics, have guessed as well. It turns out that the electrons in a wire move about 50 times slower than the speed of a snail. So the electric current propagates because the electric field in the wire moves at nearly the speed of light. The actual electrons that are disturbed by that current are bumping into other atoms all the time and other electrons, and the average rate of drift of an electron in a wire is slower than the speed of a snail. If you could count up all of those electrons, however, in a typical 1 meter or so section of wire, you'd see 6 quintillion electrons. That's 6 with 18 zeros after it. That's why I had to write this down. You'd see 6 quintillion electrons moving at slower than the speed of a snail. And these electrons are negatively charged, moving past the nucleus of atoms that they have left behind, the nuclei, and those nuclei are positively charged. And since the wire is overall neutral, it doesn't have a net electric charge. If I bring a piece of statically charged balloon that I rubbed in my hair or something, if I try to bring that near a conducting wire, that balloon won't be impacted by the current in the wire, because the wire itself is electrically neutral. But the electrons, because they're moving, and in fact, if we were to walk alongside the wire at the speed of those moving electrons, the positive nuclei appear to be submicroscopically closer together due to a very tiny but non-zero gamma. So the only way this function is exactly equal to 1 is if your velocity is 0. So 1 divided by 1 minus 0, the square root of 1 is 1. So gamma is equal to 1. Did I say 0? Yeah, gamma is equal to 1 only and exactly when your velocity in any particular frame of reference is 0. So if you're moving in a snail's pace, that's not 0. And if you apply that gamma factor to 6 quintillion protons that are ever so slightly together, what you see, due to relativistic contraction of distances, is that there's a net charge due to your motion. You see those positive charges bunching up. And you'll feel a force on the electron because those bunch up. And if you happen to have an electron outside the wire, just sitting there, it experiences that force of that combined minuscule effect from quintillions of protons and electrons moving at a snail's pace. It feels that as a magnetic force. So a magnetic force is the relativistic result of a moving electric charge. And the reason it arises is because of this gamma function. The fact that lengths and ticking clocks change their relative rates as you move. That's why magnetism exists, is because of relativity in some very deep way. That will have an effect on any charged particle moving near the wire. The charged particle sees the wire as having a charge, but only when the particle is moving. We call this magnetism. It's special relativity happening at a pace that makes a snail look like a race car. So remember how electricity and magnetism are different manifestations of the same underlying phenomena with a relativistic transformation applied to them. Magnetism is just electric phenomena with speed added to it. You've got several of these transformations in relativity. Space is interchangeable with time. Again, if you want to move through space, you give up a little bit of your motion through time relative to somebody who isn't moving along with you. If you want to move through time as fast as possible, why you'd want to do that, I don't know. But you have to stand still. So for those of you who want to gain a little bit of time in your mortal lives, just start moving a lot. You may, by virtue of that, gain a few quintillionths of a second on your lifespan.
We could live on an airplane.
That's true. We're going to talk a little bit about that later on. We're going to talk about GPS and how it's moving fast in a gravitational field. So this notion that space interchanges with time, some of you are familiar with vectors, the distance between x, y, and z coordinates in a three-dimensional space is a vector, it's a three-vector. Well, relativity says that in space-time, really, we've got a fourth component of any vector that's the speed of light times the interval, the time interval separating them. So in relativity, when you deal with electromagnetism or nearly any physical phenomena, you replace the standard vectors of physics with this four-vector for velocity that includes your motion through time. Also, there's this exchange between mass and energy. And there's an associated for momentum, where it's our regular momentum, the amount of momentum attributed to your motion relative to each of the three axes of space, as well as the amount of momentum or energy divided by velocity as the units of momentum, the amount of momentum you have through time. So this is kind of leading to one of the most challenging parts of this talk about where does E equals mc squared come from. So there's one equation, and then that's the gamma equation I showed you a moment ago. And then let's talk about this E equals mc squared. What is mass? What does it mean for something to have mass? Anytime we talk about mass, we need to think about the way we're measuring it. Now, what we often measure when we measure mass on our planet is we measure weight. When I stand on a bathroom scale and become quickly embarrassed, that scale is not actually measuring my mass, it's measuring my weight. So if I want to lose weight, I just go to a planet with less gravity. I go to Mars or the Moon. And I've lost weight. Weight and mass are not the same thing, even though we often use the same units to connote them. If I want to measure mass, there's a couple of ways to do it. I can use a balance, so I can put some known quantity of mass on one side of a balance, and then in any gravitational field, anywhere in the universe, as long as it's not zero gravity, I can put a mass on the other side and compare the two. It's not dependent upon weight. Another way that mass is measured and commonly thought about is this concept of inertial mass. It's the amount of energy or force you must expend to get a certain mass moving at a particular speed, to change its momentum by a certain value. When you're adding together speeds, let's say you've got two pool balls that are colliding. If you've got a pool ball in motion colliding with a pool ball at rest, then there's only one velocity to take into account. If you've got a pool ball moving quickly that's colliding with a pool ball that's moving slowly, then you've got two velocities to take into account. You may have two pool balls that are moving at each other and different speeds, and you've got other velocities to take into account. But there's a fairly straightforward mechanism in physics for accounting for all of these different momentums and speeds. But remember that you can never go faster than the speed of light. So what that means is that if you try to add together speeds, you have to take into account the fact that relativity is saying, if you're going a little faster than this other guy, you've got a little more gamma. You've got just a little bit more of the effects of relativity, changing what your distance and time is. If relativity changes distance and time measurements, it changes velocity measurements between two different reference frames. So the end result of that is this algebraic equation. It's not terribly complicated, but I didn't want to go through the math today. It's an algebraic equation showing how to calculate the momentum of objects that are involved in collisions while not forgetting to take into account this gamma factor. And if you solve that equation, there's a way you can manipulate it mathematically. And what you end up doing is you take this gamma function, and there's something called something related to this gamma function that's got mass in here as well. There's something called a Taylor series where you take the derivative of this, the first derivative, and then the second derivative, and then the third derivative, and then the 99,000th derivative, etc. You add them all together, and it equals the value of the function. If you take that mathematical process and you say, what is the momentum involved in any interaction between objects, you find that the momentum has the components of mc squared, mass times the velocity of light. All we have to do is add mass in here to get this, to turn this into a kind of a momentum-like measure. And you'll see that there's already a c squared buried in here. You end up with mc squared plus 1/2 mv squared plus a bunch of other terms that have to do with the ratio between v and c, between your speed and the speed of light. So a simplification of that at low speeds is that the total energy of the system is equal to mc squared plus 1/2 mv squared. Well, 1/2 mv squared has the name kinetic energy. So the total energy of the system, according to relativity, because of this gamma function that says that space and time change as you move, the total energy of a system is mc squared plus kinetic energy. So if you're not moving at all, if your speed is 0, then 1/2 m0 squared is still 0, and your total energy in your system is equal to mc squared. So mc squared is the innate amount of energy associated with any given mass at rest. Kind of makes some sense? Okay. So mass and energy change form as you're moving faster near the speed of light, or as you're approaching the speed of light. And then electric and magnetic phenomena are also in some sense interchangeable. So here's a plot of that gamma function. So that thing with the square root sign, here's what it looks like. Remember I said it looks pretty linear, pretty boring, until you get to about 90% the speed of light, and then it just goes up exponentially, like a hockey stick. So in this graph, there's this gamma, so it's the amount of change you'll see due to your speed. So you can see, in order to see a doubling of your mass, or a 1/2, things shrinking by 1/2, you'll need to be moving at 87% the speed of light. And beta goes from 0 to 1. It's how close you are to the speed of light. It's your speed versus the speed of light. So that's what this graph looks like. That's why at most velocities we will ever attain with known technological devices, we never have to worry about relativity. So what happens if the speed of light is 100 miles an hour? What if you can get on a bicycle and you're really fast and you're going down a steep hill? What happens if the speed of light were nearly 100 miles an hour? Well, a couple of things. One is you'd never be able to get close to even 75 or 80 miles an hour, because once you got to 87 miles an hour, which is 87% the speed of light, you'd have to pedal a lot harder because your mass would have increased by 2 times. Any way that you want to measure your mass, whether it's through a balance scale or whether it's from collisions, any way you want to measure your gravitational or inertial mass, you will find that your mass is twice what you expect. And in fact, to justify the fact that your mass has increased by 2 when you're going at 87 miles an hour, it means that you must have burned enough fuel from your caloric intake to equal your mass. Because that energy has to come from somewhere. So in order to get to 87% the speed of light, to get to 87 miles an hour on a bicycle, I have to put my whole mass worth of energy into that bicycle. And that energy is stored in the form, a little bit of my motion, but mostly in the form of my increased mass. Some other things would happen as you get close to the speed of light. You'd see light red shifted behind you and blue shifted in front of you. You'd actually be seared to death by X-rays as you get closer to the speed of light. So the safe velocities would be down here around 40 miles an hour, maybe 60 miles an hour, more like 5 or 10 miles an hour. So if the speed of light were different, the effects would still be the same, and you wouldn't be able to run a race like a cheetah at 60 miles an hour, but we wouldn't notice anything much different in some sense, because that would just be the world we're in. So I want to talk about a common misconception of relativity. This is one of my favorites. I don't like this graph so much. I didn't have time to make my own version of it, but I'm going to explain this in words. So, you know that nothing can go faster than the speed of light. The Andromeda galaxy, which you can see through binoculars, is 2 million light years away. If I were to get into a rocket ship, and you were to join me, and we were to ignite the engines and start a stopwatch, how long, theoretically, how fast could we get to that Andromeda galaxy that is 2 million light years away? Do you have any guesses?
What speed?
Near the speed of light. If we accelerate at 1g, we'll be going near the speed of light in about a year. So let's say that you accelerate constantly at 1g to give yourself a comfortable spaceship, and after a year you've nearly reached the speed of light. I'm not going to worry about how the engines work and whatnot. Let's just say that happens. So you're going at nearly the speed of light. The Andromeda galaxy is 2 million light years away. How long, if I start a stopwatch and I'm in that spaceship, how long before I get to the Andromeda galaxy?
50 years.
2 million years, right? Somebody says 50 years. Why do you say 50 years?
Because your watch will slow down.
You're right. You can get from here to the Andromeda galaxy in a month, if you wish. There is no limit to how far out in space we can travel in a human lifetime because of relativity. People talk about the fact that to get to the stars would require millions or thousands of years. If you had a spaceship that could withstand the forces and had enough energy, you could get from here to the edge of our observable universe in about 50 years if you accelerate constantly at 1g. So you can get 15 billion light years away in 50 human years. And if you accelerate at 1.2g, you can probably get there in about 30 years. That's the trick. Remember, it's called the theory of relativity because you can't visit your relatives again. Right. If you try to come back, so let's say I go 2 million light years away in a month, and I come back in another month, I'm accelerating at 5G or something. My face looks like this, right? If it takes me 2 months on that round trip, then I'm fine. I've had a grand old time. I've seen the Andromeda Galaxy and see that it's very much like here. But when I get back, no fewer than 4 million years must have elapsed on the planet Earth. And that's one of the problems with space travel. It's not that you can't get out there as fast as you want, given technical issues. But there's no physics reason why you can't go, why you can't traverse that distance in any amount of time you want. The problem is referring that back to somebody who stayed at rest with respect to you. And that's a clear example of this idea of time dilation. You can look at it with a couple of different things. One is your watch slows down, just like Paul said, as you're going to the Andromeda Galaxy. The other is the Andromeda Galaxy gets a lot closer because distances are foreshortened in the direction of motion. Well, since velocity is distance over time, here's an interesting thing. I have a star chart with me. I know that Andromeda is 2 million light years away. And I know that I got there in 1 year, so my speed must be 2 million light years per year, according to my local frame of reference. So this notion of the speed of light imposing a limit on velocities is absolutely true in some sense, but it doesn't constrain us in terms of our ability to move through space and time. Remember, we give up faster motion through space by having slower motion through time. As I'm going near the speed of light, if you're watching my clock on my spaceship, you'll see it go tick, 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 and you could wait a year before the next tick, right, if I'm going fast enough. So you give up motion through time to get motion through space. And that's why space-time is its own kind of thing. 4 vectors in rotation. If you move at a snail's pace through the universe, you see this is when you're accelerating. Compared to the speed of light, you're accelerating and your speed is very slow. And we can extend this notion to anything that has happened in the past. So anything that happens along these trajectories described by the boundaries made by light beams from the past and the future is what's possible to interact with in your universe. If we rescale this, we talked about measuring the universe last month. You can't ever visit or interact with anything in this region. You'd have to move faster than light. If we rescale this such that the speed of light is equal to 1, we talked about that a little bit last month, then now you've got a 45-degree angle for your past and your future. And everything you could potentially interact with in the universe, starting from a particular point, is delineated by how fast light travels. If light doesn't go fast enough to get to this stuff, there's no way you can ever interact with it. And you can think of that as your potential past and your possible future from where you are. All the rest of this is off limits. But somebody else who starts at another point in space may find that those are available. And that kind of diagram is from Hermann Minkowski. He extended it to be some cones going through space. It's the same kind of diagram except it's 3-dimensional. And as you speed up, given that this is where you are at any instant, as you speed up, what happens is, relative to some other observer, your view of possible events rotates through space-time. So what you say happens at the same time in different spaces, different places, could happen at different times in different places according to somebody else. The notion of what's simultaneous begins to be changed depending on whether you're in motion or not. So I talked about how electromagnetism is, largely the work that Einstein did for relativity was to explain electromagnetism. And Emmy Noether came up with this idea that anytime you have a symmetry, a mathematical symmetry in physics, it's got a conserved quantity. And we'll talk about that in a couple months in more depth. But the implication of Noether's theorem for relativity is that the thing that must be conserved due to the fact that the speed of light is constant for everybody, it introduces a new thing in physics, and that's called electric charge. So electric charge is in some real way a direct result of the fact that the universe has a speed limit. It introduces a new symmetry, a new constancy in nature, and that constancy manifests itself as electric charge, which also gives rise to magnetism. Now, we can talk a little bit for about 2 minutes about general relativity. I can take more questions about it in a few after the talk. But this idea that if you were sitting in a box or standing in a box, you feel the force of gravity. If you're accelerating in an elevator in empty space, you would feel the same force. Einstein recognized this as saying that inertial mass, which we talked about earlier, is the mass that you measure from any interaction, must equal the same as gravitational mass. This is a profound and surprising thing. Scientists have done all kinds of experiments to see if the mass in the equation momentum is equal to mass times velocity is the same as the mass that creates gravity. It's the amount of mass charge, if you will, that gives rise to gravitational field. Scientists have done all kinds of experiments to see if gravitational mass and inertial mass measure the same thing, and to many significant digits, they've never found a discrepancy. And the idea is that if you extend the idea of relativity in flat space-time, constant velocities, to accelerating frames, you start talking about geometries that are no longer flat. We talked a little bit about that during the math talk, how you could have non-flat or non-Euclidean geometries. You could have geometry on a baseball or on a saddle. And the idea is that these light cones that describe your possible past and your potential future, the shape and the orientation of these light cones is dictated by the local gravitational field. So you can kind of use these to map what your local gravity looks like. And this is why gravity changes what's possible in terms of your future and your past in different places, and eventually gives rise to things like the deflection of light beams around a gravitational mass, or potentially something like a black hole. Is that gravity changes what your possible future is by changing the orientation of the way light can possibly exist in your reference frame. There's this idea of space wormholes we've seen in a few movies where you can connect two distant parts of space by tunneling through a higher dimension between them. I want to spend just a second talking about GPS. So the GPS satellites are falling around the Earth at, I don't remember the speed, something like 2,000 miles an hour or something. And because they're moving fast relative to us on Earth, they lose about 7 microseconds. However, gravity causes time to change at different places as well, the relative rates of time. So in order for GPS to work, they have to factor in the fact that gravity introduces a 45 microsecond increase at the height, not because of their speed, but because of how far they are away from Earth's gravity. They're not terribly far away, but it's 45 microseconds worth of difference. So when you add in the effects of special relativity, they're moving fast, with the effects of the gravity, 38 microseconds a day would cause the GPS to drift by about 10 kilometers. Nobody wants to use a GPS if it's that inaccurate. So we see the effects of relativity in our GPS system. We see them in the black holes. Interstellar is a great movie about black holes. We see quasars. The most powerful engines known are related to black holes. Gravitational redshift. And ultimately, the entire shape of the universe is determined by gravity. Gravity tells space how to curve. and space tells mass how to move. And it's all related to relativity. Relativity was invented for things in constant motion, and then Einstein said, what about things that are accelerating? And if acceleration equals gravity, then aren't I really developing a theory of gravity when I extend this relativity idea? So that's all I had about relativity. We could continue to talk more. I want to go to lunch at Tom and Eddie's just down the street. We can stay here for a few minutes for questions. You're free to stay for that or leave or join us. And we'll reconvene back here at 1 for a little bit of board gaming if anybody's interested. So let's take some questions. Again, you're free to leave if you want, but if any questions, I'm happy to entertain them. Yeah, the movie's at the Cantera Regal 17, just down the street. We're going to see the Martin Luther King movie. I have no idea whether it's going to sell well or not because it's Martin Luther King Day, but you can potentially buy your tickets online.
What time is it?
6:55, I think.
Thank you.
Yeah.
I have a question. Does your dimensions change when you're moving close to the speed of light?
I'm not sure what you mean by your dimensions.
Yeah, like your height of
Okay.
the spaceship.
To an observer not moving with you, you look to contract in your direction of motion. And there have been all kinds of computer simulations about what this really looks like. And in some sense, it looks more akin to a rotation than it does to adjust to compression. You begin to see, like if I'm moving completely perpendicularly to you, you'll see not only that I seem to get thinner, but you'll start to see parts of my body that you wouldn't expect to see. You can treat the compression as a bit of a rotation because of the light paths from different places on the surface of the object. But yes, the short answer is yes. Your dimension is compressed in the direction of motion only. Yeah. Yes?
Talking about this increase of mass as we approach the speed of light, then are particles of light undergoing that same percent increase?
Great question. So remember, I tried to be careful to say that if you start with a speed lower than the speed of light, you can never accelerate to the speed of light. Particles of light themselves never go at any speed other than the speed of light, given exceptions about refractive index, which is kind of a fake reckoning in one way. But a photon is always going at the speed of light. And you can argue that for a photon, time never passes. Only distance changes. Photons don't move through time in their own reference frame. They only move through space. Yes?
Our new friends, Higgs bosons that create mass, are those things involved with the change in mass when speed is changed?
So anything that is entailed in the measurement or the manifestation of mass will change due to relativistic effects. So if the Higgs effect has to do with how strong a given particle couples to the Higgs field over time, well, if your time clock is changing, then that coupling will seem to change as well. So any measure of mass or any manifestation of mass will have exactly the same change due to relativity. Yes?
You may have explained this earlier, that mass increases depending on whatever criteria are involved. Are the individual parts of that mass expanding at the same rate, or what causes the mass increase?
Yeah, that's a hard question to answer. The things that make up you, if you're moving near the speed of light, you don't get bigger. You don't get more massive like a person would get massive by eating more, right? You get more massive in that the electrons and protons and neutrons that can constitute you have a greater measure of inertial mass. and gravitational mass and Higgs-derived mass. So it's the value that we measure for a given particle will change. But the particle itself, notwithstanding the foreshortening in the direction of motion, the particle itself doesn't change other than the measure of its inertial mass. The energy you're pumping in to go faster and faster, to try and get closer and closer to the speed of light, that energy in some abstract sense gets stored as additional mass through E equals mc squared, or m is equal to E over c squared. That energy that you put into moving faster gets stored by increasing your inertial mass. But it doesn't change, that in of itself does not change the geometry or the physics of what you're made of, excepting in the physics that entail measuring or accounting for the mass.
So when you look up a physics book and it tells you the mass of a proton, neutron, electron, those are rest masses.
Yes and no.
Repeat the question.
Oh, I'm sorry. So when somebody looks up in a physics book the mass of an electron, a proton, or a neutron, are those rest masses? That is a splendid question, and it has led to many delightful discoveries in physics, some of which I'll talk about when I talk about particle physics. The short answer is that for an electron, yes, it is the rest mass, although there's a long answer that kind of gets around that. For neutrons and protons, the answer in some sense is no, because neutrons and protons are composite particles made of up and down quarks. And the energy of interaction between those quarks and the speeds with which they are moving relative to one another stores a bunch of energy. In fact, the amount of energy stored because of the strong nuclear force that binds them is greater than the amount of mass that a top quark, or that an up quark and a down quark have by themselves. So when you measure the mass of a proton or a neutron, one of these composite particles, it's safe to call it the rest mass, but the stuff inside those is not at rest. It's moving at nearly the speed of light, and the energy associated with that contributes vast amounts of mass in terms of our ability to measure and interact with it. So there is relativistic mass in a proton and a neutron. The story for an electron is a little more complicated, and I'm not going to get into that right now.
I was just thinking, what you're saying is that the particles that make up the neutron proton probably give all the same answers as the electron, except they're moving so fast.
Potentially, yeah. I don't know the answer to that definitively, but I think it's plausible that that's true. I know that a vast amount of the energy or the mass associated with any charged particle, including an electron, comes from the fact that it has charge to begin with in a strange way.
Everything was the same.
Maybe. Yeah, I can't answer that definitively that everything weighs the same. I'm a little skeptical of it. If everything's made of the same kind of string stuff, maybe. It's pretty complex. Other questions? Maybe questions about general relativity, black holes, anything like that? Yep.
One thing I don't quite wrap my mind around, but it seems like classical and most physics are based on like seeing objects, not hearing,
Right.
because they have to be fixed. And yet mass seems to be a way of capturing the relationship between objects.
Yeah, so
Because science requires things to be fixed, not moving. You can't see a moving. It has to be fixed, and all the rules of science apply to it in physics or whatever. But mass seems to be somehow capturing the rules that are required for a relationship. And that's relationships are not things, they're possibilities.
yeah, you're very. You're,
I don't know if I would agree.
yeah, so the idea is that when we do many things in physics, we often talk about seeing. You see a pulley. You see a lever. you see pool balls colliding, you see a rocket ship. There's a lot of things that we talk about in physics that are predicated on our ability to literally observe them. And it may be that with regards to mass, you don't have to see in order to measure mass. And that's kind of what happens with regards to particle accelerators, right? We see the effects, the ultimate derivative effects of the fact that mass has been created in a particle accelerator by virtue of the light and the particles that eventually derive from the decay of all those other particles. We don't necessarily see them in any real sense directly. We only see their products. It kind of gets into ideas of quantum mechanics to talk about how intimately related the process of observation is with the way that the physical world exhibits itself to us or to any other system with which it interacts. When I talk about quantum mechanics next month, one of the things I want to highlight is that they often talk about an observer. An observer can be anything. An observer can be a photo detector attached to a computer. It could be a cat. It could be a human. It could be an asteroid against which a particle collides. So observers don't necessarily entail human consciousness. We'll talk about that a little bit. But yeah, you're onto something very profound, that the very nature of observation is critical to understanding really what we mean when we talk about measuring something. How are we observing it? Are we bouncing something off of it and catching it? I could close my eyes, or if I were blind, I could know that you were there by bouncing tennis balls off of you, right? So I don't have to use vision, but I do have to interact with you in some way. And the best way the most common way that we interact with things is through light. Other questions? All right, so we're going to go to lunch at Tom and Eddie's just down the street. Anybody wants to join us? Thank you again. See you next month for quantum mechanics.